Hello and welcome to the Digital Spiffy YouTube channel. This video is the second in a series covering the material on the CCNP ENCOR exam. I will be using physical Cisco equipment to lab the material. The lab material is sourced from the CCNP ENCOR Lab Manual version 8. I highly recommend reading the CCNP Enterprise Core 350-401 official cert guide in conjunction with this lab material. This will provide a better understanding of the labs and what is occurring on the equipment. You can find links to these books in the description below. This video will be covering spanning tree and provide an overview of how switches become aware of other switches and prevent forwarding loops. A reliable network provides redundancy. Multiple switches and multiple links between them safeguard a network from single points of failure. Redundancy is considered best practice, but requires specific configurations to prevent network loops. Loops can occur with broadcasts forwarding continuously until the link becomes saturated. In a packet that crosses a layer 3 boundary, a mechanism called time to live is used to limit the lifespan of that packet. This does not occur at layer 2, and traffic can be forwarded over and over until a switch processor crashes. In this screenshot of a packet capture, I've simulated a network loop with the 3 switches we will use in this lab. In our terminal output, you can see that the CPU recognizes that processor consumption is high and provides the process that is consuming resources. Spanning tree protocol provides a process for the switch to recognize other switches through the advertisement and receipt of bridge protocol data units. STP builds a loop-free topology by blocking redundant ports from sending traffic. STP operates by choosing a root switch and deciding which ports should not forward traffic. There are multiple versions of STP, but in this video, we will be covering 802.1d, which is the original specification, per VLAN spanning tree, which is a Cisco proprietary protocol, and 802.1w, known as rapid spanning tree. There are several key terms involved in spanning tree protocol. It is essential that we understand what each term means for setting up STP. The root bridge is the most important switch in STP. All ports are in a forwarding state. The switch is the top of the spanning tree for all path calculations done by other switches. A root bridge will have all its ports in the designated port type. Bridge protocol data unit is a packet used for switches to determine a hierarchy and notify of changes in the topology. BPDU uses the destination MAC address of 0180C2000000. There are 2 types of BPDUs. Configuration BPDU. This BPDU type is used to identify the root bridge, root ports, designated ports, and blocking ports. The configuration BPDU consists of the following fields: STP type, root path cost, root bridge identifier, local bridge identifier, max age, hello time, and forward delay. The other type of BPDU is the topology change notification. This BPDU type is used to communicate changes in the layer 2 topology to other switches. Root path cost is the combined cost for a specific path towards the root switch. System priority is a 4-bit value that indicates the preference for a switch to be root bridge. The default is 32,768. System ID extension is a 12-bit value that indicates the VLAN that the BPDU correlates to. The system priority and system ID extension are combined as part of the switch's identification of the root bridge. Root bridge identifier is a combination of the root bridge system MAC address, system ID extension, and system priority of the root bridge. Local bridge identifier is a combination of the local switch's bridge system MAC address, system ID extension, and system priority of the root bridge. Max age is the maximum length of time that passes before a bridge port saves its BPDU information. The default value is 20 seconds, but the value can be configured with the command spanning tree VLAN, VLAN ID, max-age, max age. If a switch loses contact with the BPDU source, it assumes that BPDU information is still valid for the duration of the max age timer. Hello time is the time that a BPDU is advertised out of a port. The default is 2 seconds, but the value can be configured from 1 to 10 seconds with the command spanning tree VLAN, VLAN ID hello time, hello time. 802.1d STP delivers assistance for a loop-free topology on one VLAN. 802.1d has port states that each port will transition between. Using default timers, the time it takes a port to enter the forwarding state is approximately 30 seconds. The port states are as follows. Disabled. The port is shut down or admin down. Blocking. The port is enabled, but traffic is not being forwarded to prevent a loop. This port will still receive BPDUs from other switches, but no modification of the MAC address table will take place as normal traffic is blocked. Listening. The port has moved from blocking and can now send or receive BPDUs. The time that is spent in this state is set by the STP forwarding time. Learning. The port can modify the MAC address table based on the traffic it receives. The port will not forward any network traffic except BPDUs. The time that is spent in this state is also set by the STP forwarding time. Forwarding. The port can forward all network traffic and can update the MAC address table as expected. This is the final state for a port that is expected to forward traffic. Broken. The switch has detected a configuration or an operations problem on a port that can have major effects. The port discards packets as long as the problem exists. 802.1d spanning tree protocol has 3 port types. The root port is a network port that is connected to the root bridge. The switch will have one root port unless it's on the root bridge. Designated port. This port will send and receive BPDUs with other switches. A root bridge will have all its ports with this type. Non-root switches will use this port type for ports connected to other non-root switches. This port type ensures that downstream switches have connectivity to the root bridge. Blocking port. A network port that is not forwarding traffic because of STP calculations. STP uses a cost system for root path calculation. The cost is based on the link speed of the interface. The root path is determined based on the cumulative interface STP cost. We've covered the bases for the original specification of spanning tree. Now we can configure our lab equipment and implement spanning tree. If you are able to follow along with Packet Tracer, CML, GNS3, or physical equipment, I'll be using 3 Cisco switches and 1 Windows PC. So we'll start configuring our switches, and let's do the D1 switch first and set the host name. Go ahead and configure the console terminal. And now we can configure the per VLAN spanning tree mode. So we just do the spanning tree mode PVST, and this is the default for modern Cisco switches. So now we can do our trunk interfaces. And we'll allow VLAN 1 and 2, and we'll just leave 1 as the native VLAN for these trunks. And now we can do our VLANs. Now we can configure our PC1 with the correct IP address for VLAN 2. And if you did notice, on A1 we're connected to port 024 and we're using the switch port access VLAN 2. So we just need to set the IP address for this PC based on that VLAN. And a quick way to get to the network adapter settings on Windows machines is from the command prompt. Do the ncpa.cpl, and you can do this from the search bar. We can also do it from the command line like I just did. So we'll just set our IP address here. And we're going to use VLAN 2 network, and we'll just set it to a IP address that we know is not being used. And again, the default gateway is going to be that D1 VLAN 2 interface. So we'll just verify here we have that IP address set. And this adapter you can just ignore, that's how I'm remoted into this computer, to the Wi-Fi. But we should be able to ping the VLAN 2 interface on D1. And it'll take a second to reach the network, but you can see now we're able to ping PC1 to the VLAN 2 gateway. Here's a quick look at our network diagram, and we've got our trunk ports configured. We've got our PC1 set up for the access port on VLAN 2 for A1, and I can give you a physical view of this is what the equipment is actually looking like. And this is port 24, this is our PC. Here's our trunk interfaces between each switch. This switch is the D1 switch, has a fiber connection for gigabit to the D2 switch. Here's a quick look at the configuration I have set up on these switches, and I'll have the link in the description for these files on my website, so if you want to get a better look at them, I'll provide this configuration file as well as the photos that I've shown, and you can get some more information if I'm going a little bit too fast for you. The switches have been configured and interfaces enabled. Spanning tree protocol is operational using the default settings, and we're using the per VLAN spanning tree. We have a loop-free topology with redundant connections, and in this part of the lab we'll discover what the default spanning tree looks like and determine why it has converged the way it did. The first step is to locate the root bridge. As a switch is initialized, it assumes that it is the root bridge. A BPDU is crafted using the local bridge identifier. The switch will listen for BPDUs from its neighboring switches and calculates who is the root bridge. We can locate the root bridge with the command show spanning tree root. D1 is the root bridge in this lab, but this output may look different in your lab. The root bridge is determined by the system priority. This 4-bit value indicates the preference for a switch to be root bridge. The default value is 32,768. In this command output we can see the root ID. This is D1's local bridge ID, but presented as the root on each switch. As you can see, D1's priority is 32,769 on VLAN 1 and 32,770 on VLAN 2. This is because the default system priority is added to the VLAN number to set the system ID extension for each VLAN on the switch. And we are missing VLAN 2 on D2, so we'll go ahead and just populate that. In the command output on D2 and A1, you can see the system priority is the same using the command show spanning tree. This is because we are on default settings, so you might be wondering how was D1 elected the root bridge if the system priority is the same on all switches. STP deems a switch preferable if the priority in the bridge identifier is lower than the priority of the other switch's configuration BPDUs. If this is tied, the MAC address from the bridge ID is used. This is a combination of the switch's system MAC address, system ID extension, and system priority. And if you go back and look at our key terms, you can kind of get a better idea of what I'm talking about here. But in the root bridge identifier, the MAC addresses are compared, and the smallest converted binary number wins. And we can see the system MAC address with the command show version, and you'll just pipe the include MAC address. Looking at the MAC address for D1, we see the MAC address is 000F23774600. Looking at D2's MAC address and A1's, if we convert the first two octets into binary, you can see that D1 has the lowest binary number, thus the root bridge identifier on D1 is more preferred. We have determined why D1 was chosen as the root bridge. Now we can view the root ports and see what path traffic is taking to the root bridge from the non-root switches. The root port is a networking port that is connected to the root bridge. The switch will have one root port unless it is the root bridge. This port is the lowest path cost to the root bridge. Path cost is the total the port cost in the path to the root bridge. The port cost is based on the bandwidth value of the port, and I've created a table based on the port cost that you can see up here in the top right. And if you check each port cost in the show spanning tree output, you can see that gigabit ports are 4 and fast Ethernet ports are 19. D2 and A1 are directly connected to D2, our root bridge, so in this case port cost and path cost are the same. You can see the cost of each interface with the show spanning tree command. In order to see the path cost change, we will shut down the interface connecting D1 and D2. This will force D2 to calculate a new path to the root bridge. So we'll go ahead and do that now. After shutting down the gigabit port on D2, you can run the command show spanning tree again and see the cost in the upper portion of the output change. The cost was 4 and now it's 38. This is because D2 must now go through two 100 megabit ports to reach the root bridge. So 19 plus 19 is 38. Designated ports are ports that will send and receive BPDUs with other switches. A root bridge will have all its ports with this type. Non-root switches will use this port type for ports connected to other non-root switches. This port type ensures that downstream switches have connectivity to the root bridge. For the next step, we will bring the gigabit 101 port on D2 back online. This will restore our full topology and allow for the non-root attached links to exist. On D2, you can issue the command show spanning tree after we bring this port back online and see the change. You'll have to wait until the port status is forwarding. And if you remember from before, we talked about the ports transitioning based on the STP forwarding timer. So you can see here it's in listening. We'll run the command again. It's in learn. So it's listening for the BPDUs, it's learning. Give it some more time here. And now it's in the forwarding state. If you take a look at the A1 switch and issue the command show spanning tree, you'll see that ports 01 and 02 in VLAN 1 are in the alternate role in Cisco per VLAN spanning tree. This is the equivalent of the 802.1d discarding port state. These interfaces are up and receiving BPDUs from the designated ports on each segment, but they will not learn MAC addresses or forward traffic until they stop receiving BPDUs and transition to the designated role. D2 is controlling the designated port status for these ports connected to A1. Because D2 has that lower cost to the root bridge, it's going to be in control of these ports for A1. So designated port role on D2 and the alternate or blocking port role on A1. So on A1, ports 01, 02 are in the blocking status. Each switch can only have a single root port to ensure that loops don't occur. If A1 lost direct connection to D1 on ports 13 and 14, port 02 would only take over if port 01 were to fail. The decision about which interface is used is based on the lowest port priority, which defaults to 128 plus the interface ID number. So the higher the port, the less likely that it's going to become the root port. So again, if 13 and 14 were going to fail and A1 had to calculate a new path to the root bridge, it would take a look at 01 and 02, and 01 would be the choice because of this port priority. In this lab, we are using per VLAN spanning tree. Per VLAN spanning tree will take a decent amount of time for the ports to transition once the topology change BPDU is received. On D2, we can shut down the gigabit Ethernet port that connects to D1, and D2 will calculate a new root port based on the port priority and cost. We can see this occur by issuing the debug spanning tree events command, and then we'll just go ahead and shut down the gigabit Ethernet port. And you'll see from this debugging output the time it takes D2 to calculate a new path to the root port via fast Ethernet 101. In the last part of this lab, we will implement Rapid Spanning Tree Protocol. Rapid Spanning Tree is also known as 802.1W, and I like to just remember this by calling it Wicked Fast Spanning Tree. Rapid Spanning Tree speeds up the convergence time for the transition of ports. On D1, we can change the spanning tree mode to Rapid per VLAN spanning tree with the command spanning tree mode rapid PVST. And we'll just go ahead and do that on D2. Rapid per VLAN spanning tree is backwards compatible with 802.1D, so it can transition ports, but it'll take that slower amount of time if the other switch is running the 802.1D. So we can bring back our gigabit Ethernet port now that both D1 and D2 are running rapid per VLAN spanning tree. You'll see the amount of time that it takes the ports to transition is significantly faster on this protocol. Thank you for watching the Digital Spiffy YouTube channel. This video is the second in a series covering the material on the CCNP ENCOR exam. In this video, we explored the spanning tree protocol.